Today we're going to look at geometric sequences and exponential functions. It turns out a geometric sequence leads right into an exponential function. Let's remember what a geometric sequence is. A geometric sequence is one created by multiplication. For example, I could start at 4, and then every time I move one spot in this example, I multiply by 2. Over and over and over, I repeatedly multiply by 2. That 2 is called the common ratio. Notice that 8 divided by 4 is 2. A ratio is a fraction. 16 divided by 8 is 2. Every fraction I make, when I divide those numbers, I get 2. Current divided by previous. Remember how we numbered these? We called the first one a sub 1, the second one a sub 2. The subscript means which position is it in? A sub 5 is in the 5th number in the sequence. Remember that we could find any number in the list by observing the pattern. If we're looking for a sub 10, the 10th term in this list, we know the list starts at 4. We know that every time we move one position, we multiply by 2. Because 4 is the first term in that list, I only need to move 9 places in the list to get to the 10th term. I multiply by 2 9 times to get to the 10th term. This is going to be a large number, 2048. This pattern right here is what we see when we look at an exponential equation. We can make this a little bit friendlier to use in an exponential equation. If we change the numbers in our list, change the 1, 2, 3, 4, and 5, and call them a sub 0, a sub 1, a sub 2, a sub 3, a sub 4. Numbering it this way allows us to use those numbers 0, 1, 2, 3, and 4 as exponents. Take a look at the table below. Notice how, starting at 1, that 8, the y value, is 4 times 2. That's what we did up here. We took 4 times 2 to get 8. And that 16 actually ends up being 4 times 2 times 2, because we moved one spot in the sequence, we multiplied by 2 again, and that's 4 times 2 squared. And see how now the x is the exponent? And 32 is 4 times 2 times 2 times 2. We moved one spot in the sequence, we multiplied by 2 again, and that's 4 times 2 to the third, and our x is 3. And 64 is 4 times 2 to the fourth, and again, our x is 4. Now notice this is where it gets interesting. It turns out that the first 4 is actually 4 times 2 to the power of 0. And you have to remember that 2 to the 0th, in fact, any number to the 0th power is 1. 10 to the 0th is 1. 1 million to the 0th is 1. And 0.1 to the 0th is 1. So when I take 4 times 2 to the 0th is 1, and 1 times 4 is 4. Look at the patterns in this table. 4 is what we started with. Every one of these starts with a 4. 2 is what we multiplied by. It was the common ratio. And then we went to the power of x, where x is the number of times we multiply by 2 to get that number in the position in the sequence, knowing that we called our first term a sub 0. Here's that table again. In general, an exponential equation is of the form y equal the start. Now when I say start, that means it's the y-intercept. Look, we started at 4 and 0, 4. When x is 0, I'm on the y-axis and I'm up at 4. That's the y-intercept. This is the y-intercept. Times 1 plus r, where r is the rate. It's the percentage that you're growing by, to the power of x, where x is usually time. Now, this is a weird table here. If I think of it as 1 plus r, notice how our common ratio, which is 1 plus the rate, is actually 2. That's what we're multiplying by. That's the common ratio over and over and over. 2, 1 plus r is 2, means that r is 1, meaning you're growing by 100%. Now, look at the numbers again and think about this. 100% of 4 is 4, and 4 plus 4 is 8. 100% of 8 is 8, and 8 plus 8 is 16. 100% of 16 is 16, and 16 plus 16 is 32. You're growing by 100%. When you multiply by 2 and you double something, you only grow 100%. We need some examples to understand this better. Take a look at this table. 0, 20, 130, 245. This is a geometric sequence right there. 20, 30, 45, 67.5. You're multiplying by the same thing every time you step forward one position. The equation for this would be y equal to start. That's the y-intercept. It would be y equal 20 times 1 plus 0.5 to the power of x, where x is usually time. We talk about a real world situation. Now, notice that the common ratio is 1.5. 30 divided by 20, 1.5. 45 divided by 30, 1.5 again. 67.5 divided by 45, yes, it's 1.5. And 1.5 is 1 plus 0.5. And I'm telling you here that your rate is 0.5, and that is 50%. Now look at these numbers. What's 50% of 20? 50% of 20 is half of 20, it's 10, and 10 plus 20 is 30. What's 50% of 30? Half of 30 is 15, that's 50%. 15 plus 30 is 45. 50% of 45 is 22.5, and 22.5 plus 45 is 67.5. You're growing by 50% every time you multiply by 1.5. This equation would be written as y equal 20 times 1.5 to the power of x. Look at the table below. I just want you to understand where these numbers come from. 20, 30, 45, 67.5 is a geometric sequence, but as an exponential equation, we look at this like 20 times 1.5 to the 0th, because anything to the 0th power is 1, and 1 times 20 is 20. The next one is 20 times 1.5 to the first power. That makes 30. The next one is 20 times 1.5 to the second power. That makes 45. Every time I move forward, I add another 1.5, and again, the x is the exponent. Let's take a look at how this will work with a real-world situation. When I apply this equation to the real world, I have to understand that it could either be growth, meaning my numbers are getting bigger, or decay, my numbers are getting smaller. What's the difference then? Growth means your rate, the percent you're growing by, is a positive percent. 1.5, that was growth, because every time we multiplied by 1.5, we increased 50%. Decay means your rate is less than 1. For example, if I told you the rate was negative 20%, that means you'd be losing 20% every time you step forward one position. 1 plus r, that's the common ratio. In the previous example, remember it was 1.5. Here, if it was negative 20%, it'd be 1 plus negative 0.2. 20% is 0.2. It would end up being 0.8. 1 plus negative 0.2 is 0.8. And if I gave you a number like 100, and I said, oh, let's make a geometric sequence, multiplying by 0.8 gives you 80. And you threw away 20%. If I multiplied by 0.8 again, I would get 64. And you threw away 20% again. Losing 16, going from 80 to 64, means you threw away 20%. It's just gone. And if I multiplied by 0.8 again, I'd get the next number in the list times 0.8. That would be 51.2. Every time I multiply by 0.8, 20% gets thrown away. I'm decreasing by 20%. Rather than a geometric sequence, though, we're looking at this as a table, and it's an exponential equation that describes it. 80 was 100 times 0.8 to the first power. 64 was 100 times 0.8 to the second power. 51.2 was 100 times 0.8 to the third power. And in fact, 100 is 100 times 0.8 to the 0th power, because anything to the 0th power is 1, and 1 times 100 is 100. Here's an example of both growth and decay. The population of elk is growing at 2% each year exponentially. If there were approximately 17,000 elk in the year 2000 and the growth rate remains constant each year, determine the approximate number of elk in the year 2018. Our equation is y equal the start. We're starting with 17,000 times 1 plus the rate, and it's growing at 2%. You have to understand that 2% is 0.02. Move the decimal 2 places. 1 plus 0.02 is 1.02 to the power of x, where x is time. Now we just need to figure out the time. We have the year 2000 that things began, that was the start, and the year 2018, and that would be 18 years, 2018 minus 2000. So the x is 18. We punch that in the calculator and round to whatever the question says, and I believe this one said round to the nearest elk, the nearest whole number. It ended up being 24,280 elk. The next example is decay. A certain medicine decays at a rate of 11%. If a patient took a dose of 300 milligrams, that's the starting dose. You're starting at 300. Notice it's start. Times 1 plus the rate. Well, it's decaying. That means it's decreasing. So it's 1 minus the rate. 1 minus 0.11 to the power of x, which is time. And that would be 15 here. It's in hours. Now we would write this as y equal 300. 1 minus 0.11 is 0.89 to the power of 15. Enter that in your calculator. And you might be asked to round to the 10th here or the whole number. Do whatever the question says. I'm going to round to the 10th on this one. 52.2 milligrams. Notice how we did this again. It was y equal to start, which was 17,000 here and 300 here. 1 plus the rate. 1 plus 0.02 was 0.02 because it was growth. You were increasing. And below, it was 1 minus because it was decaying. It was decreasing. 1 minus 0.11 for 11%. And then to the power of time. Question 10 is review. Notice that when we make these equations, how close they are to what we do when we do exponential equations. Common ratio is current divided by previous. It's the 1 plus r in an exponential equation. Here, negative 15 divided by negative 5, or negative 45 divided by negative 15. Every case, it makes 3. For the next one, negative 16 divided by negative 4. Pick any pair, take the current divided by the previous. You're going to get 4 for this one. On the third one, 25 divided by 5 is 3, just like 125 divided by 25 is 3. And on the last one, current divided by previous gives you 2. This is a sequence of numbers, a list of numbers, and we're going to find the fifth one. The sequence starts at 5, Every time you move one spot, you multiply by 3. 5 is the first number in the list. I only have to move 4 positions to get to the fifth term. 1, 2, 3, 4. That ends up being negative 405. The next one starts at negative 4. Every time you move one spot, you multiply by 4. To get to the fifth term, we only have to move 4 places from the first term. That ends up being negative 1024. The next one begins at 5. When we move one spot, we multiply by 3. Because we're starting at the first term, we only have to move 4 places to get to the fifth term. That one ends up being 405. And the last one, it begins at 9. When you move one position, you multiply by 2. 9 is the first spot. We need to move 4 places to get to that fifth spot. And the answer is 144. Question 11 is so that you get an understanding of what an exponential graph looks like. This is just y equal 3 to the x. You could think it as y equal 1 times 3 to the x, meaning you're starting at 1, and every time you move one spot, you multiply by 3. Fill out the table, put in 0. 3 to the 0 is 1. Anything to the 0th power is 1. 3 to the first is 3. And 3 to the second, 3 times 3 is 9. In WAMAP, you only need 2 points to graph this thing. Click on 2 points and drag, and you're done. I have to hand draw this. That's a little more difficult. 0, 1, that's our intercept. Remember, that is the intercept, the start. 1, 3, and 2, 9. 3 cubed would be 27. I'm off my graph. It's way up there somewhere. And let's just point out that 3 to the negative first is actually 1 over 3 to the first. Remember that reciprocal idea we talked about with negative powers? So when x is negative 1, you get 1/3. Gets close very quickly. When x is negative 2, that's 1 over 3 to the second, which is 1 over 9. At negative 2, you're 1/9, which is really close to 0. Your graph should look something like that. It'll be easier to graph in WAMAP. Just click on the 2 points. Question 13 asks you whether this is linear or whether it's exponential. Linear means you'd be, say, adding 8 every time, adding 8. We can see that's clearly not the case. Exponential means that you have a common ratio. And we know that common ratio is the current divided by the previous. So look at your y values. 10 divided by 2 is 5. 50 divided by 10 is 5. 250 divided by 50 is 5. The common ratio is 5. This table is exponential with a common ratio of 5. The next 3 terms in the sequence of y values, we're multiplying by 5. So take 250 times 5, and we get 1,250. Multiply that by 5, and we get 6,250. And multiply that by 5, and we get 31,250. What is the equation of the function? We know that it's y equal to start times 1 plus r to the power of x, where x is time. Sometimes they'll use t for an exponent. This is the common ratio. Our equation here then is y equal to start, that's the y-intercept, 0, 2, y equal 2 times 1 plus r, that's the common ratio, it's what we multiply by, which is 5. That means the rate, by the way, is 4 or 400%, to the power of x. Question 15. We're going to write two sets of equations for these tables. The first question in the pull-down box is whether this is growth or decay. Look at the numbers. Are they increasing or decreasing? 100, 90, 81, that would be decay. They are decreasing. The y-intercept is when x is 0. That's when you're on the y-axis when x is 0. It's 100 here. The common ratio, remember that the common ratio is current divided by previous. So look at your table values, pick one, any pair, and take a current divided by a previous. 81 divided by 90 is 0.9. 90 divided by 100 is also 0.9. What is the formula then? We know that it's y equal the start times 1 plus r to the power of x, where 1 plus r is the common ratio. Y equal 100 times 0.9 to the power of x. For your next one, is it growth or is it decay? Looks like the numbers are increasing. That would be called growth. The y-intercept, that's when x is 0, is 50. The common ratio is current divided by previous. How about 55 divided by 50? That's 1.1. Notice that this again is 1 plus r, meaning that r is 0.1. Multiplying by 1.1 increases whatever you're multiplying by 10%. The formula is y equal to start, that's 50, the y-intercept, times 1 plus the rate, that's 1.1, to the power of x. Question 17. Here's some values for a function. They're calling it f. Verify your results. Remember that f of x is just another name for y. You can put a y there anytime you want. That's x and y. Verify your results with a graphing calculator. You don't need to do that. Let's find the equation. Is it linear, first of all? Are you increasing by a constant? If you were, you'd be adding 12 here and you'd be adding 12 there. That does not appear to be the case. If it's exponential, then there's a common ratio. The common ratio is current divided by previous. 16 divided by 4 is 4. 64 divided by 16 is 4. 256 divided by 64 is 4. This thing is definitely exponential, and the common ratio is 4. We know our equation is y equal to start, where that's the y-intercept, times 1 plus the rate to the power of x. This is the common ratio. Here it will be y equal 4, that's our y-intercept, 0, 4, times our common ratio of 4. Every time I step forward one spot, I multiply by 4 to the power of x. Question 19, we get to apply our equation. Y equal to start times 1 plus the rate to the power of x. If we have decay or the values are decreasing, then the rate will be negative. Here we have y equal to start. There were approximately 8,000 blackberries in the year 2000. 8,000 times 1 plus r, and our rate is 4%. That's 1 plus 0.04, which is 1.04, to the power of x, where x is time. This was beginning in 2000, and we're looking for 2017. That would be 17 years to the power of 17. And I would just enter this in the calculator. 8,000 times 1.04 to the power of 17. The question says round to the nearest whole number. This ends up being 15,583 bears. Question 20. The population of foxes is decaying at 11% each year exponentially. Y equal to start times 1 plus the rate to the power of x. If there are approximately 15,000 in 2020 and the growth rate remains constant each year, determine the approximate number of foxes in the year 2026. You're starting with 15,000 and it's decaying, it's decreasing. So it's 1 plus a negative rate or 1 minus the rate, 1 minus 0.11. We have to figure out the time. We began in 2020. And we're looking for the population in 2026. Subtract those. That's to the power of 6 years. This is y equal 15,000 times 0.89 to the power of 6. And that ends up being, to the nearest whole number, 7,455 foxes. This one's like the example in the teaching video. We'll take our standard form of an exponential equation and plug in our numbers. The medicine decays at 5%. The starting dose is 800 milligrams. And it's decaying, it's decreasing, so it's 1 minus 5% is 0.05. 5%, yes, that's 0.05. Now keep in mind, 50% would be 0.50 or 0.5. Keep in mind, when you make a number a percent, a whole number, the decimal is right there at the end of it, and you move it 2 places, 1, 2, which is why it becomes 0.05. 800 times 1 minus 5% to the power of 5 hours. 5 is our time, it's in hours. This is y equal 800 times 0.95 to the power of 5, and we're rounding to the nearest whole number again. We get 619 milligrams. Question 23 is another decay problem. A vehicle purchased for $29,800 depreciates at a constant rate of 4%. Depreciates means it goes down in value. Determine the approximate value of the vehicle after 11 years. Y equal to start times 1 plus r, and our r is going to be negative here, to the power of x. This is y equal 29,800 times 1 plus negative 4%, or 1 minus 4%, which is 0.04. Remember that 0.4 is 40%, to the power of 11. We're going to round to the nearest cent, which means you're going to have 2 decimals. We can simplify this to y equal 29,800 times 0.96 to the power of 11. And that ends up being 19019.532. Now I'm writing the 2 just to point out this is the digit we look at to round to the nearest cent. The 2 tells us to keep that 3 the same. So our answer then is $19,019.53.